we have two branches of work. We focus on research and also on industry adoption. And on the left here, you can see research. That's a lot of working with academics, focusing on building out Alberta as a leader in artificial intelligence and machine learning. But most of my work is with industry. And that's a lot of the focus of what I'm going to talk about today. We're a nonprofit, and we want to help organizations figure out if machine learning is right for them. And if it is, how do they start going down that path? These two things feed into each other. They really help build out our province's ecosystem in that way. And so the project I'm going to talk about today, it's doing water treatment, and it really bridges both of these aspects. It's an industry application, useful in the real world, but it's relying on some cutting edge research. So my goals in talking today are to give you a better idea of how to identify reinforcement learning problems in the real world. A lot of work in machine learning doesn't use reinforcement learning when it comes to the real world, but it's helpful to be able to see these problems. And then I also am going to talk a bit about the complexity of reinforcement learning problems. I want to provide some idea of how you can tell if a reinforcement learning problem in the real world is going to be fairly easy to approach or more of a challenging problem. So in order to talk about those things, I'm going to give you an idea of what reinforcement learning looks like, and then talk about some examples of some value generating applications. And in this picture here, that's a water treatment plant. As I'm speaking right now, there's a reinforcement learning agent running on that water treatment plant in Drayton Valley, Alberta. It's making decisions and learning how to make water treatment more efficient. So before I dive too much into that project, what does reinforcement learning look like in the real world? How would you know if you saw a problem domain that fit reinforcement learning? Well, there are a lot of technical details about reinforcement learning. There's an environment and a state. You may hear about a Markov decision process, but that's not what I'm going to cover today. There are lots of great talks on that topic. They're really interesting, but I really want to emphasize this focus on how to identify these problems to know if the business value is actually there and if the problem is a good fit. And specifically in Alberta, where we have a lot of opportunity for industrial control, I think it's valuable to think about where these problems show up in industrial control contexts. So before I dive into the reinforcement learning aspect, I want to contrast it with supervised learning. Now, I think most of us have encountered supervised learning, maybe done some projects in the area, so I don't want to get too far into this, except as a contrast with reinforcement learning. So in supervised learning, we're generally focused on making predictions, one thing at a time. Like we have this house, maybe some information about the house, and we want to know what price it will sell at. We may do this in a big batch looking at many houses, but the focus is still on each house as an individual. They're completely independent as separate houses. Or we might be thinking about what product a customer might purchase. And in that case, we're looking at individual customers. And we're also not thinking about a series of purchases. It's not if this customer purchased one product, what's the next product they might purchase and how would that influence their future purchasing? It's largely about one prediction about that customer. Similarly, you might have some photos. What animal is in this picture? Each photo you predict is not influencing what you're predicting in all the other photos. So a lot of these, they're like a pair of questions and answers, like Jeopardy. You present a question and you get your answer. And this is really valuable. A lot of industry applications, a recent survey said, I think 90% of companies that adopt machine learning are specifically using supervised learning. So this is really valuable. I think of a spy agency, and the supervised learning is a bit like an analyst. They're there to provide factual information and make predictions based on the data that we have. And this is essential. Every good spy agency needs a whole team of analysts who are providing these predictions. But you don't want to send these analysts out into the field. If you send an analyst out into the field, you've either got some cheesy action movie or a dead analyst. This is not a good situation. And this is where I see reinforcement learning is coming in. Reinforcement learning, instead of having an analyst, you have an agent. Someone that's going to go into a situation and take actions and think about the long term. What's the effect of this action and the next thing I do and the next, and how is that going to impact my ultimate mission? And I said I wasn't going to get into the technical details, but actually agent is the technical term that we use in reinforcement learning for the AI that goes out and does things, that takes actions and deals with the consequences in this long-term sense. So let's make this a bit more concrete and pull it back to this water treatment plant. In this picture, that's this water treatment plant in Drayton Valley. And on the left, you can see that vertical gray box in the background. That has a filter inside it. So we take in river water, send it through the filter to clean the water and get clean tap water out of it. So this is on the end of cleaning water for people to use, not on the sewage side of water treatment. So our goal here is to produce as much clean water as possible while keeping our maintenance costs and our chemical costs low. So if you think about an agent in this situation, the agent has to decide, am I going to just focus on cleaning and cleaning and cleaning and cleaning water? Or am I going to stop occasionally? Sometimes the filter starts building up with a lot of dirt. As you're passing water through, it has to filter out the dirt. And so you actually need to spend some of your precious clean water to rinse it in reverse to clean off that filter, and then you can keep going. So a foolish agent might decide to never do these rinses. And then it might end up with a filter that looks like this, full of dirt and clay and all clogged up. So we can choose this short-term, long-term trade-off. Do I run cleaning 24/7, or do I stop every hour to rinse off and try and prevent this? And being in this dynamic situation where moment to moment, the AI has to decide whether it's going to focus on producing more of what it needs to do or deal with maintenance, this is a reinforcement learning scenario, the opportunity to consider the consequences of my actions. So if I overgeneralize and kind of split supervised learning and reinforcement learning, I can say that supervised learning is about making predictions, while reinforcement learning is about taking actions. Now, this isn't entirely true. Supervised learning, you could set it up to suggest actions. Maybe it's a prediction that's in a pipeline that's going to make actions, or maybe the supervised learning itself is predicting the best action to take. And on the other side, reinforcement learning agents can actually make predictions. They're generally predictions about the actions that would be taken, like an analyst predicting if we take this action and another organization takes another action, what do we predict the cascade of effects that will happen of different people acting in different ways? So there is some back and forth on this where they blend a little bit, but the key thing that I want to focus on when we think about using reinforcement learning for industrial control is that reinforcement learning, we're trying to train an agent, something that's going to go out into a situation and do something there. And it's specifically there to optimize the outcome of many actions, looking at the long term so that over a period of time, it's optimizing these actions. And it's doing all of this in a dynamic situation where it has to respond to whatever's going on around it. So let's say that you find your industry application and you look at it and you think, you know, this could be a setting for reinforcement learning. My problem here is this sequence of actions with some type of long-term goal. So now what do I do? Well, the question is whether reinforcement learning is going to be an easy win or a more challenging thing to apply in that situation. So I want to talk about some value-generating applications for RL. In what context is reinforcement learning most likely to be really successful for something in industry? So the first category I think about, I'm going to talk about 4 of them. And the first one is mimicking a human expert. So it's especially useful in this case to replace humans if they're doing a task that's really dirty and uncomfortable for humans, or a dangerous task that really ideally we would want to keep humans safe and not send them into this scenario. or just something that's boring. Humans don't want to do it, or they're not attentive enough to keep doing it. Those are great opportunities, but it still has to be the right scenario where the reinforcement learning can be successful. So if we just want to mimic human experts, then we can treat this somewhat similarly to supervised learning and other forms of machine learning, in that we can just use piles of historical data and use that to train something that could work really well for replacing the human experts. Now, the challenge here is that this type of reinforcement learning agent isn't likely to improvise. It's not likely going to figure out how to adapt to new and unusual situations that didn't show up in the historical data or didn't show up very often. And it's also not likely to learn to do better than the humans. It may occasionally figure out how to make use of different human experiences and improve, but probably it's just going to kind of match the baseline of whatever the data shows. I think of this kind of like in this spy agency, a trainee or a junior agent who you can put out in the field and they'll do all right if they're encountering a scenario that their mentor prepared them for and that they maybe experienced before. But as soon as it's something different, they freeze up and don't succeed. So this is a good opportunity. What about on the water project? When I'm treating water, can I use this to run a water treatment plant? Well, this one's not really working for my scenario. We really want to improve beyond what the humans do. The humans, they'll adjust chemical doses and settings at most a couple times a week, usually less often, because they're very busy with more important aspects of running the plant. But there's a lot of opportunity here to optimize and save more money and be more efficient if we could change these parameters daily or hourly or even faster. So we want to do something even more efficient than human actions. So for my use case, I kept looking. So another opportunity is to use a simulator. This can be really useful if you have this accurate simulator of your real world scenario, often called a digital twin in industry. One recent example was a nuclear fusion reactor. There was a need to control some things 10,000 times a second. Obviously, no human has reflexes that fast, so you're going to need some type of AI or fast control system for it. And there were some approaches that were very laboriously hand-coded or like designed by reverse engineering a whole bunch of equations to figure out when the plasma inside of this nuclear reactor needed to be shaped in certain ways. And that worked. They were able to manage that. But then they tried training a reinforcement learning agent. And it was able to control this very complex system for twice as long as the previous approaches. And it could handle more complex situations that the previously designed approaches had not been able to handle. But the key here is that they had an extremely accurate simulator. The physics inside fusion reactors like this are very well known. There are lots of great, very accurate equations to describe how plasma moves inside of a reactor. So they were able to build this simulator that would represent the situation, so they could then build this reinforcement learning agent to deal with that situation. That's not always an option. It's often not an option. Even when we build digital twins, they're often based on machine learning models that are using historical data, and they can't generalize enough to different situations and really reflect the true underlying processes going on. So it's questionable whether a simulator will work. If it's based on underlying equations, a lot more likely to be successful. So in the case of water treatment, we looked into building a simulator, found that based on historical data, this just wasn't accurate enough. The simulator was not able to reflect the real world conditions. So we moved on. A third approach is if you can multiply your learning across many locations at the same time, send out your agents all over the place, and through collaborative learning, they can figure out what to do. So in Alberta, I think of oil wells. We have over 150,000 active oil wells in our province. So maybe at each of these wells, we need to like push down a chemical or add some water or change a pumping rate. I'm not an expert in oil. I don't know exactly what might be optimized in this scenario. But if we came up with some parameters to optimize, then we could potentially try it on thousands of wells. And the engineers who design these industrial controllers, they make them to be extremely safe. They know the range of parameters that are safe in different situations. And a lot of times we're able to then look those up. So at the water treatment plant, I know that certain chemicals I can dose at a rate of 0 to 10 milliliters every minute. And as long as I'm in that range, I'm not going to cause any problems with the system. I might reduce the efficiency if I'm not adding enough chemical and I need to slow down my process, or I might just waste money by adding more chemical than is needed. But I know the safe range. So I could potentially send a whole bunch of junior agents out into these scenarios with limited training. And at first, they're going to make some mistakes. They're going to waste a bit of money with extra chemicals. And that's really the cost of developing any system. You spend a bit of money up front for the long-term gains. And the long-term gains here are that these agents eventually learn to optimize beyond humans at a faster time scale or closer to the most optimal process and the most optimal efficiency. And then that produces the lifetime of savings. So the key here is having thousands of opportunities for agents to learn all at the same time in a setting where the engineering design shows this range of operation that we can act in to find more optimal settings. And this is a fantastic opportunity for industrial control. I think in Alberta, we have a lot of opportunities for this. But the problem, once again, for water treatment is I only have one plant. There are many plants across Alberta, but many of them use different processes. The underlying technology is different between different locations. So we can't necessarily run these agents all at once across many of them and hope to learn from it. So we'll focus on this one plant. But then what do? I want superhuman control, so I can't just learn from the historical data. I can't build a simulator because the underlying equations aren't well known, and we're doing some new and unique things. And I only have one learning environment, so I can't multiply my learning across locations. Well, in this case, I've moved into more of a research level problem. And this is still absolutely possible. This field is growing and expanding every day. And there's much bigger opportunity for disruption in this situation because we're using some of the cutting edge research, some of the expertise that Alberta is really at the forefront of. We are well known for our reinforcement learning skill. So there's a great opportunity here to be involved in these even more complex problems. And that's how we've been seeing success on this water treatment plant. We currently have agents running. We adjust chemical doses to optimize. In the next few weeks, we're launching even more of these agents to learn more about how to optimize different settings and controls. And a key for this kind of partnership is that you need academic experts alongside the industry partners, water treatment experts right alongside the reinforcement learning experts, whether that's a team from a university or hiring the PhDs who have a lot of skill in that area. But when moving into this category of these research level problems, those kind of partnerships are what really drive success. So to summarize, reinforcement learning, oversimplified, is about training an agent to optimize the outcome of many different actions. And it's going to do this over a time period, looking toward the long-term goals, all in a dynamic, complex, changing situation. And if you find a problem that looks like this kind of problem, and you want to see if you can optimize these actions in some way, then it may be valuable to mimic a human expert to duplicate what the humans are doing. Or maybe you can build a simulator, and with that simulator, create a really powerful agent. Or take advantage of multiple locations that can all learn these agents at once in a system that has clear constraints and understanding of the situation. And even if those situations aren't all fully true, you can still dive into it, and there's great opportunity for industry disruption and really changing the way things are done by moving into these research level problems. So that's that's what I have to share today. I can take some questions. I've also got my contact info on here in case you want to talk about this project or reinforcement learning or machine learning in general.
Hello there, can you hear me?
Yes.
Excellent. So I have a good question myself about, I enjoyed your comment about trusting the engineering control limits. Not a lot of people in the public necessarily believe that as a statement, but as working in the industry, it seems like a very rational thing. Are there times where it's easier to trust the limits? There was one time we operated $1 billion plant blind for about 8 hours for various reasons. But we had just done safety commissioning the month before, so we had a lot of confidence. Are there times you'd trust the control limits less?
Yeah, I think a key here is really talking to those engineers and the designers and explaining what's going on and understanding what that context is, right? Like sometimes they've created the safety constraints to apply when a skilled operator is running it, but they haven't thought about, well, what if someone's being a little more careless? And so there's definitely, I think it's mostly just about a conversation because the engineers who designed it, they do understand what the constraints are. But you can't go into it blindly.
Is there any limitation on the number of decisions an agent can or should make?
Not really. The idea with reinforcement learning is that you're making a long-term sequence. So sometimes this is a limited length. Maybe you're only doing 5 or 10 in a row. But like in the water treatment context, we're designing this to be an infinite time. Like it should be able to run until the machine, like until the plant breaks down. So you just adjust your problem solution based on the time horizon.
Okay. How would you more measure the performance or the success of reinforcement learning models?
Yeah, so that inherent to reinforcement learning is you have to have an idea of what the goal is, because that's how you teach the agent if it's successful and it learns. So when you formulate what your goal is, which in the water treatment plant, maybe I just have an equation of dollars. And I say, the more water you create, you get dollars for creating water. And when you do maintenance, you lose dollars for doing maintenance. And then its success is just the dollar value that it's generated over time. So for different problems, you'd make that differently, but you're basically creating this equation of long-term value.
Sounds good. The next question I have is from Parinaz, and I'm not the best on my pronunciation here. But how's the pipeline for this kind of learning look like for process plants?
Yeah, that has been a challenge because a lot of tools for other machine learning approaches don't assume that you need the data real-time streaming one second at a time or whatever your time interval is. So often it's batched. So we've been building a lot of this more from like first principles or earlier design ideas. So I don't really have documentation. I think there could be more work done in making these pipelines a little easier.
Okay. And yeah, I know from my experience, getting it into the public domain, sometimes there's proprietary reasons not to, or even legal ones.
Yeah, we do have a couple of like news articles out there, I guess, and we're working on papers we'll be publishing, though not specifically about the pipeline.
Okay. A question from Wish, and that is, have you explored deep learning in this area?
We may end up there. In the early stages, we feel like a lot of simpler approaches are likely to be successful. Some of it we have been using some neural networks for some of the prediction aspects of the project. But we think starting simpler and then progressively getting more advanced is in general a good approach.
Sounds good. Can you explain a little bit about how you built the environment for the water treatment problem?
Yeah, there was a lot of background software engineering it was like a legacy SCADA system, and we needed to bring all of that old data into a a more modern software architecture with continuously streaming data. And then from there, we wrapped it in some kind of standard like code interfaces that would be used to just run a regular reinforcement learning agent.
Okay. And Mark may have asked a related question here. I'm stretching my PLC knowledge on this one, and that is to say, if it's the same question, how is this technically executed?
Yeah, so we basically talk to the PLC. Once per second, we read hundreds or thousands of tags. And then from there, that's in our own system, and we're interacting with it in our own system. And when we want to take an action, we write a new set point to the PLC. We don't touch down at the level of PIDs. That's a little lower than we want to go. But yeah, it's all talking back and forth with the PLC on an external computer with way more processing power.
So can a reinforcement learning agent control the entire process?
Hopefully one day. Right now, we're doing one section at a time, and we're looking, because some of the challenges, there are different time horizons on different things that we're looking at. Like replacing a filter, you might do every year or multiple years, whereas other things you can actually measure on a shorter time scale. So we're starting on the shorter time scale to get faster results, eventually maybe hopefully controlling the whole plant.
So some things are currently only manipulated by humans. What kind of things should you consider when you actually determine if you let an agent do it, or can you even legally let an agent do it?
Yeah, we're definitely talking with the operators about which things to control. So right now, this project, it's not on the main plant. We have a smaller research plant. So we can do whatever we want. And at worst, we waste a lot of money by damaging our research plant. But humans never drink this water yet. But we are definitely leaning toward the kind of things that the operators say, oh, there's a lot of leeway, you can adjust that. I don't know that I would ever give it control over safety things without at least having a human in the loop to say yes or no.
So more a SCADA type supervisory role.
Yeah.
Okay, Carl asks, what issues have you realized when it comes to streaming data? What about statistical stationarity? Stationarity is a word I've not used before.
Like a lot of our issues with streaming data have just been getting it to come in at the right speed and figuring out if it's synchronizing back and forth properly, like if there's a lag inside the PLC or in our code. But I like a lot of that I do think is kind of straightforward software engineering aspects, even if it's not as common in the reinforcement learning field, especially academically. But there are definitely a lot of standard tools for this. For statistical stationarity, we do. So if I'm reading the question right, we do have scenarios like different seasons where the water comes in very differently. Like right now, I know in Edmonton, our water tastes like chlorine because this time of year is different than other times of year. And so part of our thoughts about training is dealing with this idea that seasonally and yearly, there may be a shift in the environment. And that's why you need a reinforcement learning agent that can actually adapt in real time and is not just executing some predetermined policy.
And if we misinterpreted Carl's question, he can clarify, because yes, spring turbidity in the water does dramatically change water treatment. Good, nice basic question from Jan, actually, and that is, can you explain the difference between simulator and machine learning?
Yeah, so like when it comes to digital twins, a lot of times machine learning is used to build something similar to a simulator. I think that's what you're asking about. And in that case, usually it's about like, what's the historical data showing? And then how can we use that to predict what might go on in the situation? Whereas I think of a simulator as being really based on fundamental underlying equations. You can use the term in both places. So this is maybe my own distinction in the definition here. But a machine learning approach is based on the data rather than models and equations.
And I think a final question from myself, and that is along the order of the simulator digital twin thing, which was as I've read over the last few years, cures all the world's problems. They're magical. It sounds to me like you're a little bit more measured on your respect for them, and they're difficult to build a really good digital twin.
Yeah, the challenge is a digital twin most likely is only going to represent what it's seen before. So if this is the range your human operators have acted in, then the digital twin can reproduce that probably pretty well. But what if optimal is a little bit over here? What, like in water treatment, for example, the operators tend to overdose. They put too much chemicals in. And they do that because they don't want people to get sick. So they have to be conservative and they can't go in there and change it every hour. So they need to add a little more to keep it safe. But we know that it's more optimal to add a bit less. And a digital twin could not reflect that because there's just no historical data of that being done before.
Okay. Mark actually does have a question. We're not cutting questions off on purpose by time here. And that is, if the learning's adjusting set points in the PID loops, how does this compare with a cascade control loop? And which could accomplish something similar?
So I'm not very familiar with cascade control loops. But I can say a key for reinforcement learning is that you can give it a higher level goal. Like I'm guessing to give a cascade control loop this like long-term thing of like based on changing water conditions, we still want to maintain our output and we can't model that, right? We don't know how it's going to change in the future, but we know what the goal is. Then the agent can optimize toward that goal and more dynamically respond to it. So most of the traditional approaches I've encountered require a lot more understanding of processes, or they're more simpler and smaller scale.